Okay, so let's look at this one. Shown below is a conducting rod that slides along the metal rails. The apparatus is in a uniform magnetic field of strength 0.25 Tesla, which is directed into the page. The rod is pulled to the right at a speed of 5 meters per second by a force F. The only significant resistance is the 2 ohm resistor shown. What is the EMF induced in the circuit? So the induced EMF is again BVL, and L is just this portion of the rod, okay, the portion that's part of the circuit. All right, so B is 0.25 Tesla. It's being pulled at 5 meters per second times 4 centimeters, that many meters. Okay. And so this works out to, that is 1, 5 times 10 minus 2. 5 times 10 minus 2 volts equal to 50 millivolts. So that's the induced EMF. Okay, now let's calculate, do part B. What is the induced current? The induced current is induced EMF divided by resistance, 50 millivolts divided by 2 ohms equal to 25 milliamps. Okay, and then what is the magnitude of the force? Now, the power output, which is power out equal to power in. Okay, by doing the work in pulling the rod, you're converting your input energy into output electrical energy. Power output is EI, and that should equal force times velocity. Okay, so the force is EI or velocity. Okay, let me add a page. Okay, so the force you're applying is EI over velocity equal to the induced EMF is 50 millivolts. I is 25 milliamps divided by the velocity is 5 meters per second. Okay, so the force is 50. The 5 cancels. 50 times 5 is 250, and milli times milli is micro. And this is 10 minus 3, and that's 10 minus 3. So into 10 minus 6, and volt times amperes, of course, is so this is newtons. That's a force. Hang on a second. So volts times ampere is joules. No, joules per second. Anyway, it's volts, ampere, meter per second. That gives you newtons. Okay, so this is that many newtons. So you have to apply a force of 250 micronewton to pull this to the right. What are the power output of okay, let me go back to C. All right, I guess so this, in reading the problem, here's how they want us to solve this problem, really. Okay, so let's figure out the direction of the current first. Now, what Mr. Lenz tells you is, so the magnetic field is into the sheet of the paper, and as this is being pulled out, the flux into the sheet is increasing into the sheet. So what we want to do is the induced current needs to produce a field that opposes that increase. So we need the induced field to come out of the paper. All right, and for that to happen, the current needs to be in that direction. When the current is in this direction, the current feels a magnetic force I cross L, I cross B, feels a force, the magnetic force in this direction. And the applied force needs to be equal and opposite to that. Okay, so the magnetic force is ILB. Okay, so here, so the applied force should equal the magnetic force, which is equal to ILB. Okay, and we solve for the current. We have the current 25 milliamps. The length is 4 centimeters, and the magnetic field is 0.25 Tesla. Okay, so that's how they wanted us to calculate the applied force. Okay, and so this is equal to, that's 100, that kills that, 0.25 and amp, oops, and so this will work out too. There's a milli, and all other units are, so millinewtons is what it'll work out as, 0.25 millinewton. Okay, and what are the power output of F and the power dissipated in the resistor? Okay, now we'll calculate the power. Page below. Okay, so what is the power output and power dissipated in the resistor? Okay, so the power actually is FV, and that's equal to 0.25 into 10 minus 3 newtons times the velocity, and the velocity is what is the velocity? 5 meters per second. And this works out to 5 times 0.25 is 1.25 into 10 minus 3 watts. Okay, milliwatts, and let's make sure that the electrical power is matches that power. Is equal to VI, and the induced EMF is 50 millivolts. Induced current is 25 milliamps, and this thing is 5 times 25 is 125, so watts, 1250 into 10 to the minus 6 watts equal to 1.25 into 10 minus 3 watts. So as expected, power in is equal to power out. Okay, that takes care of this problem.